So today, I want to start applying some of these techniques using integrals so that we can define other things which could typically be very difficult to define abstractly. So, question for you. I have here a curve, C, connecting point P0 to point P1. How long is it? That's not an intuitively obvious question. But we do know how to take the distance between 2 points, right? If I had a straight line, the length of that line segment comes from the distance formula, from Pythagoras. That's easy. So how can I take that and apply it somehow to help me figure out the length of that curvy thing over there, C? Because this formula only works perfectly straight lines. Well, line segments. The mean value theorem would allow me to take an average, right? And it would say, okay, well, I could go from here to here and say that that's the average, but what if this wiggled back and forth a lot? Then that distance would be a lot different than the straight line distance, wouldn't it? And so while the straight line would give me an average, it wouldn't help me find the actual distance. Wait a minute. When we did the mean value theorem, we used velocity to figure out distances, right? So I know my velocity times time, that's distance, right? And I can think of the velocity as a tangent line moving from place to place. So what if we actually used little lines instead of the curve? I'm going to do a gross oversimplification, like we did with our integrals. I'm estimating. Let's pick a finite number instead of rectangles, just subdivisions. Let's break this curve up into a bunch of pieces. I've just added 3 dots. So I have this point, which will be x0, y0. I have this new point, which will be x1, y1. And then here I'll have x2, y2, and x3, y3, and x4, y4. Right? And instead of trying to do the curve, let's replace each piece of the curve with a piece of a straight line. That's not quite going to be the same distance, but it's going to be close, isn't it? So now I can say for each of these little pieces, I can use this formula. Which means in order to find an approximation for the length of this curve, I could say, oh, I want the total of the length from xi, yi to xi plus 1, yi plus 1. And those lengths get done this way. And we'll go, I goes from 0 to 3. Or we could go from 1 to 4 and change the way we do the indices. That would approximate my value, wouldn't it? I'm adding a bunch of stuff up. When I did areas under curves, I added up a bunch of little rectangles, didn't I? Well, now I'm adding up a bunch of little distances. Adding up a bunch of little rectangles gave me an integral. Adding a bunch of little distances should give me another integral. The question is, what's a formula for that L? Well, let's use that L right there. That's L, the distance formula, just like we wrote over there on the right. I'm going to mess with this. I'm going to do a little weird algebra here. I'm going to divide by xi plus 1 minus xi squared. And then I'm going to multiply by it. So I'm going to multiply by 1. But I'm going to write it like this. Now it's kind of weird to look at here, but what I did is I divided both of these fractions by xi minus 1, xi plus 1 minus xi squared, and then I multiplied by it out here. So these would cancel, and I really just multiplied by 1. What's that fraction? Yeah. That is 1. This expression is the change in x, isn't it? xi plus 1 minus xi, that's change in x. Let's write it delta x. Now that makes over there in the right-hand most fraction, that makes the bottom of that delta x squared also. In that same idea, what's the top of this fraction? That's delta y. Exactly, Jack. Now here's something even better. These are being multiplied, right? This thing squared times this set of parentheses. That's squared, but it's under a square root. What happens? So I should just get a delta x. But then this stuff is not squared, so it's got to stay. And I have 1 minus. Look at that. Those are both squared top and bottom, aren't they? So I could write the whole fraction squared. So after quite a bit of messy looking algebra, I have the following idea. That what I want to do is I want to add up this expression for all these little pieces of straight line that we saw slide down back in this picture. Right? So I really want to think of doing a sum of all of these things. But if I'm doing a sum, I could let the little distance get smaller and smaller, right? If I let the little distance get smaller and smaller, I get a better and better estimate. Page 544. Here's their version of the picture I came up with. But what I really want is I want this picture in the bottom left corner here. And it shows that as I use more and more and more points, this set of line segments gets closer and closer and closer to the actual curve, doesn't it? So really, I would like to know what's going on here as delta x goes to 0. I've seen this thing before. Limit as delta x goes to 0 of a sum of something that looks like that. Where is my sense of deja vu coming from? That looks like a Riemann sum. If that looks like a Riemann sum, then what that really is an integral. Integral of what? The integral of the square root of 1 minus change in y over change in x. What calculus thing is that? Except it's squared dx. I have to start somewhere and end somewhere. Oh, I'm starting at the x value for point 0, and I'm ending at the x value for point 1 all the way at the other end of the curve. This integral is the length of our curve. Now, problem number 1 is that because there's a big square root in here, this integral might not be easy. But even if this integral is easy, how the hell do I know if it works or not? Let's see if we got this idea right. I'm going to do a straight line. My curve is a straight line. Straight lines are nice and easy. If x equals -1, what's the y value here? F of -1 is? And f of 4 is? So I can think of this as going from -1, 1 to 4, 11 in a straight line. How long is that line segment?
It's like you have to go to Pythagoras and say x squared plus y squared root now.
Let's do that. By Pythagoras.
It would be square root of 5 squared.
Oh,
plus square root of 10 squared.
Let me write it out. Four minus -1 squared plus 11 minus 1 squared. So you're right, this is 5 squared and this is 10 squared. So that's 125, right? Perfect. Now, I let's try the integral version. This formula up here for the length of our curve should give me the exact same result. So I've written down the formula again, so we have it in front of us. Advantage number one, f prime is really simple, isn't it? Derivative of 3 plus 2x is 2. So I'm integrating from -1 to 4, square root of 1 plus 2 squared dx. That's the integral from -1 to 4 of the square root of 5. That's a number, right? What's the antiderivative of a number?
The number times x.
And then I evaluate between 4 and -1. Well, that means I put in the 4, I put in the 1. 4 minus -1, that's 5 square root 5. But up here I have the square root of 125, yes? But 125 is 25 times 5.
It could be like 5 and. It could be like 5 and 5.
Which is exactly the same bloody thing. Hallelujah, it worked. Jack, you're looking at that like it bothers you. Talk to me.
It doesn't, I can't. One letter, yeah, no, that's better, thank you.
You're welcome. I have a Zoom button, we can use it. I have crappy handwriting too, which doesn't help. Now, the best part about this is that this works for any function. The worst part about this is that it could result in an integral that is absolutely disgusting that I don't know how to do. So the problem is that there's a square root in there, and that means when I go to do this integral, the antiderivative, like this, may turn out to suck. If it does, if this integral turns out to be absolutely psychotic, I have two different choices. What could I do to make my life easier if I end up with an integral like this that's nasty? Promise that's not rhetorical. No. I can start looking at all my integral tricks, right? I could do a U substitution. I could do integration by parts. I could do a bunch of weird algebra in the middle. I could do a trig sub. I could really go over to the tables. I could, if I really got stuck, I throw it on the computer. Or I could just do it numerically. And do the trapezoid rule or Simpson's rule. If all I want's the answer, what's the number here, then doing this numerically might work. If I need to know what the actual procedure is, then I might actually want to do it the long way. And it might be easier to do the antiderivative with whatever tricks I've got there. Questions? Please note, I did this problem that we just looked at by writing this as 1 plus f prime of x squared, right? And I got that because of what I did back here, where I pulled out the delta x. I'm going to draw you a different picture, a hugely different picture. I'm going to say, let's look at the point 1, negative 1, and the point 11, 4. What did I do compared to the problem we were just looking at? How are these points related to the points we had in the previous part? Leah?
I was thinking the 11, 4 would be similar, but instead of being negative 1, it goes 1, negative 1, so that looks like it's before it was.
Before it was negative 1, 1, and it was 4, 11.
At the lower end, it's like backwards.
It's exactly backwards. All I did was switch the y and the x, right? I'm going to go a step further, and I'm going to change the labels on the axes. If I did the same problem, now my horizontal variable is y, not x. It would be the exact same problem, but you're doing it with respect to the letter y. So if we, instead of thinking about a function written as y equals f of x, we could think about a function written x equals g of y. And then my length formula becomes 1 plus g prime of y squared dy instead of x. Really what I'm thinking about is I'm thinking about doing my problem up and down instead of doing it from side to side. And some of our graphs work better left to right, and some of our graphs work better up and down. Like this example here, it's written x equals y squared. So it's written as a function of y rather than as a function of x. That's perfectly fine. I can do the exact same sort of problem. Instead of chopping up my graph this way, I'm chopping up my graph vertically. Now, quite literally, this is a reflected version of the previous picture. So whereas the previous picture went this way, now it goes this way. But it's really the same graph, you just turned your head. So it depends on which way our formula is given to us and which way the integration becomes easier. There's a new trick now for me. Instead of thinking of everything as having to be integrated in x, sometimes I can switch the equation and see what we do in y. We did this last semester in Calc 1. Anybody remember? No? Hang on. Back in chapter 6, we did areas between curves. Remember areas between curves? Chapter 6, section 1, we had problems that looked like this, the area between two curves. And I said, this works really well, and a bunch of our pictures were, oh, I got a top and a bottom. Yes? I also had pictures where instead of having a top and a bottom, I had a left and a right. So instead of cutting this up with respect to x, I cut it up with respect to y. These two problems here on page 434 were done slicing in y rather than slicing in x. We did this for our volumes as well. Remember, we did disks and washers, and sometimes we did them around the x-axis, and sometimes we did them around the y-axis. And depending on which way we were going, we got stuff with respect to x, or I promise there's a picture. We got stuff with respect to y. So here, I'm thinking of that same idea as we did back in chapter 6. But it's really going to depend on when we look at the integral, which way is it written? Which way is it going to be presented to us? That'll help us determine whether it's easier to do. So, for example, this problem is given to me with its limits in terms of x. It's given to me as an equation, y equals stuff in x. I'm pretty sure I'm going to want to do this one the way we just looked at with f prime of x dx. Because everything is written in terms of x. My limits are in terms of x. I think this problem is going to be easier to do in x. But there's a loaded statement. I think it's going to be easier. It doesn't say easy, but it does say easier. Let's see if we can do this one. What is f prime of x? Little algebra is necessary to get there from here. Hold that thought, Leo. Talk to me, Leo.
I was thinking to take the root of y first.
Yep, what do you get?
The first, and it would be 1/2 x squared. And the minus 1/2 x to minus 2.
Aha. Because remember, the derivative of x cubed is 3x squared. So I'm going to get 3x squared over 6, and the 3 and the 6 will cancel. But I need to write this as 1/2 x to the negative 1. That's where I get this. Okay. I don't like having negative powers, so that's y prime. Let's keep going. Y prime is 1/2 x squared minus 1 over 2x squared, because the x to the negative 2 goes in the bottom. So far, so good? Okay. Common denominator. I need an x to the squared on the bottom here. So I'm going to write this as x to the 4th over 2x squared minus 1 over 2x squared. That's a single thing. Now, why did I do that? I did that because I'm going to need to square this derivative. Remember, my goal is to do the derivative, the integral of 1 plus f prime, well, might as well write y prime, squared dx. So we need to figure out what that square root is. So let's do that. I need to take this and square it. Please notice, as is the case with most calculus problems, the big ugly stuff is the algebra. It's going right in the side of my head and making me very cold. So when I square this, the bottom becomes 4x to the 4th. What do I get on top? Beautiful. I'm subtracting, I need a common denominator. What's my common denominator? Oh, say again? Right, 4. Okay. I just noticed though that I made a typo. It's 1 plus, not 1 minus. So it helps if I write down the right thing. So then, yes, you'll write 4x to the 4th plus x to the 8th minus 2x to the 4th plus 1 all over 4x to the 4th. I like that. We'll write it 4x to the 4th over 4x to the 4th. That's perfect. Wait a minute, I have like terms. What happens? And what do I get?
2x to the 4th.
Okay, wait a second. That looks almost exactly like this, doesn't it? The only difference is that middle sign, right? And we got this by multiplying this out. And that means that this factors. It's a square. And it's not just any square, it's x to the 4th plus 1 squared. Whereas the other one was x to the 4th minus 1 squared. They rigged the algebra for me. Oh, thank God. Because what happens? That thing goes under a square root. My goal now is to integrate the square root of this. I didn't write something down. What are the limits on that integral? Where did we start and where did we end our piece of curve? Say again? That was the other one. This one. That was the other problem. In this case, 1/2 to 1. So from 1/2 to 1. But what happens here? I'm taking the square root of a bunch of stuff that's squared. What's the square root of 4? And the square root of x to the 4th?
X squared.
So the bottom is just 2x squared. And now I'm back to the same sort of setup I was algebraically. I split this up, I get x squared over 2 plus 1 over 2x squared. I know how to integrate this. It's power rule. I know what to do. Hey, you're unhappy. Talk to me. From here to here or from here to here? Okay, so x to the 4th over 2x squared. The 2 stays, but x to the 4th over x squared is x squared. Subtract the powers, right? And then 1 over 2x squared. So just split it into 2 fractions. That's power rule. That's the integral of 1/2 x squared plus 1/2 x to the minus 2. What's the antiderivative of x squared?
1/3 x cubed.
But I also have a 1/2, so it's 1/6 x cubed. Antiderivative of x to the negative 2 is x to the negative 1 over negative 1. I get a minus sign instead of a plus. And now I can plug in my numbers. When I plug in 1, 1 minus 1/2, 1 raised to any power is 1. Minus, I put in a half. 1/6 times 1/2 cubed. when you cube something that's a fraction, you cube the top, cube the bottom. So that's 1 cubed, which is 1, over 2 cubed, that's an eighth, 1/2, 1/2 to the negative 1. Exactly. You flip it, right? It's in the bottom. You take it out, you flip it over. That's a 2. And now I can actually work out what this value is. You can use a calculator if you want. I get 1/6 minus 1/2 minus 1 over 48 plus 1. Which, if I stick that into a calculator, I get some nasty looking decimal, 0.645833, da 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 da. If you do it as a fraction, you get 31 over 48. Because you can do a common denominator there. Whew. Wow. Okay, first of all, that was not pretty. But all the unpretty parts were algebra parts. Actual calculus was taking a power rule derivative and doing a power rule integral. It was all the algebra in between that sucked. Not bad. Second, most of the time, if I'm stuck doing something like this, and I'm really, really grinding for an answer, I'll plug it into a computer. But if I actually want to be able to do this integral, I need all the tricks we used before. In this case, only power calculus I did was the power rule. Questions? One of the problems we will have is that sometimes these integrals simply don't work. I would like you to find the length of the sine curve from 0 to 2 pi. This is a picture we all know and, well, some of us love, some of us hate. But this picture looks just like that. And now I'm asking you to tell me how long this is. And you might think to yourself, that's not a difficult question. These are related to circles. This answer should somehow be related to circles. Unfortunately, when I go to set up the integral, remember my length will be the integral from 0 to 2 pi, 1 plus y prime squared dx. What's y prime?
Cosine x. Yeah.
Which means I'm going to get 1 plus cosine squared. The unfortunate part of this next step is that no matter what trick I try, that doesn't have a nice antiderivative. I went to my computer and I said, I would like you to integrate this for me, please. And I got back this. My computer choked on it. This is an elliptic integral of the first type. There is no known antiderivative that we can write in terms of functions you already know. This is royally and thoroughly impossible for me to do. So what do? Oh, I can do it numerically. The answer is 7.64. But I can't do that without Simpson's rule or the trapezoid rule or some other approximation like that, because the antiderivative gives me this elliptic integral formula. I literally do not know how to write that down in terms of anything other than an integral, and that's not helpful. So the unfortunate part is that I don't know how to do this problem. I know it can be done. I just don't know what the answer is as an antiderivative. My goal is to never give you problems that look like that. I want my problems to be rigged enough that we can actually do them. Questions? I go for a drive on the highway. I see every mile a little green sign on the side of the road that says what my mile marker is, right? They're even at, most of them are every 10th of a mile. 73.2 or 87.6 or whatever it is as I go down the highway. I would like to figure out a way along a curve that I could use the idea to measure where I am as I'm going. Let's pick a starting point. I'm going to define a new function. I'm going to define the function s of x. And I'm going to define it in terms of an integral. That expression over there on the right is our arc length, isn't it? This is called an arc length integral. Now, why would I do this? Well, here's the best part. If I integrate from a to 1, this answer tells me how far I've gone when x got to 1. This is a distance traveled. This is my odometer. This is my mile marker. This tells me how far I've gone. A sneaky comment for you. Fundamental theorem of calculus. What's s prime of x? Fundamental theorem of calculus, part 1. I'm taking the derivative of an integral. I know the fundamental theorem of calculus was a long time ago, but we did cover it. And when I do that, it turns out when you take the derivative of an integral, you just replace the variable on the inside with the variable at the top there. That's what the fundamental theorem of calculus tells me to do. If you move the dx to the other side, you get ds equals the square root 1 plus f prime of x squared dx. Isn't this exactly what I was integrating with my arc length? So rather frequently, I will write, and we can use, the arc length is the integral from a to b ds. And this expression is called an arc length differential. There are several more examples of working out arc lengths in this section of the textbook. I think all of them are useful exercises for you to read through because they will help you follow the integral tricks we've been doing, and we'll use them. Now there's more, and there's more stuff I'm going to do with arc length. This ds is going to come back over and over this semester. We'll use it next week and the week after and the week after that, several different places. But we won't do any of that until Monday, because tomorrow is the exam. We'll see you all then. I'm going to my office hours shortly, and then there's the review session as well. So if you've got questions, come see me, go see Mia or Reese, and then I will see you all tomorrow for the exam. The keys will be posted in about another minute and a half for the review sheet and the homeworks. Have a good day, everybody.